Hello and welcome everybody to session number 9 of my lecture on statistical energy analysis and hybrid methods. Okay, this time I would like to talk about inhomogeneous wave equations and all the methods how to solve this, and the results of this will be the capability to do some sound radiation calculation or the sound field calculation of vibrating surfaces. To be honest, this will be a tough chapter, lots of theory, but if that helps, lots of useful, hopefully useful theory. Anyhow, let's dig into the details. When we set up the wave equation, we use the homogeneous version. So it means in our equation of continuity, we neglected the source term, here the mass flow in this case, as you can see here. And we did the same for the Newton equation, or the impulse equation, where we neglected the force on the force density term that affects the velocity of our cube that we took for our force balance. So this is something that we did not include in the first derivation of the wave equation. Anyhow, this time we will use it, and the steps are exactly the same, and we end up with a classical wave equation as we know it here in time domain still. And on top of that, we get a source term, which is a combination of the mass flow and, or this time the mass flow rate, and the gradient of the force coming from the operation that we need to derive the wave equation out of this. Good. We modify things a little bit, so we replace the density source by our already well-known volume source strength density. That means now we have a volume source, and to make a mass source out of it, we just need the density of fluid, which is, in this case, could be the density of air. Again, we are usually not solving this in time domain, so we convert all this into the frequency domain, and then we end up with the so-called inhomogeneous Helmholtz equation. Again, the classical wave equation, or the Helmholtz equation as we know it, plus an extra term. And when we combine both terms in one term, we call this here f function fq, or f index q. This is something that we call the source term of our inhomogeneous Helmholtz equation. Good. The question is, how can we solve such systems? And that's might be quite a complicated thing, but we use some of the solutions of elementary sources that we have already derived. Before we do so, we create, or we use a function that we call the green function, and this is defined by the following inhomogeneous wave equation. So this is the solution of the inhomogeneous wave equation with a delta function as in space, three-dimensional delta function as space as a source term. So three-dimensional, that means we need, which is simply the product of a delta function in all spatial dimensions. And r with the vector r or r0 are just given by the three-dimensional coordinate x, y, z, or x, y, z, 0, index 0 in the space domain. So as we know, there is a specific, the delta function is mainly, the properties are mainly defined in terms of an integral, and all the things that were stated in the system session also hold for the spatial arrangement. So we can use the sifting property. So if we have a function in three-dimensional space and the delta function in three-dimensional space, this sifts out the value at r. And also the volume integral of the delta function, if the position is inside this volume, is simply 1. So what is the solution of the above thing? The solution of this is something that we already know, that is our famous point source. So the green function is given by this expression in the frequency domain, using omitting the exponential j omega t factor for the frequency time dependence, and the distance L is just the absolute value of the difference between both vectors, or the distance between both positions. Good, so far for the classical simple green function, but this is not enough because we need some freedom in the choice of our green function. And this is done by adding any additional solution of the homogeneous wave equation. So this is okay because the solution of the homogeneous wave equation is always 0. That means we can add it to any existing green function. And this is what we do. So we just take our well-defined normal green function, add our arbitrary function to this, and then we get the so-called generalized green function. Don't question this too much. You will later see why this is needed and how this can be interpreted, and why we finally need an additional generalized green function. This will become much clearer based on an example. So again, as already stated, the purpose of this could be, for instance, to get some extra freedom or free options to fulfill specific boundary conditions. Again, this also will be shown in later examples. Good. So we now come back to what we are looking solutions for. This is the inhomogeneous wave equation. So this is where we need a solution for any complicated spatial distribution of sources. It could be a propeller, it could be loudspeakers somewhere, it could be a vibrating surface, and so on and so on. So again, the generalized green function must be a solution of for the special case, where we assume that both vectors are part of a volume. This will be better shown on the next slide. And that we have some specific conditions also at the boundary of this volume, a boundary that we denote by partial symbol and volume. So, and this is again the solution of the inhomogeneous version with our delta function as source term. Good. In order to perform or to receive some kind of a global solution, the next step is to take the green function multiplied by this expression minus the pressure distribution or the solution multiplied by the generalized green function. So what do we get at the end of this? We get the following expression. So that means we have a quite complicated term combining the green function and the pressure Laplace operators and so on. We don't have to go too much into the details, but this is the outcome of the expression that we had now. It's important to note that all operations are evaluated in a specific volume that we are interested in. It could be a room, it could be the cavity of a church, the cavity of a machine, or whatever. It has always a specific boundary. We have normal vectors at these boundaries, and very important, all our space vectors must be inside this volume. You might wonder, okay, what do I have if I have to calculate free space? This is not an issue. If you have to calculate an infinite space, this one part of the boundary could be positioned somewhere in infinity. This you will also see in a later example. Good. We exchange in this expression r and r index 0 and perform an integration of this over this specific volume V. And then we get this expression here, which goes step by step and rearranging things a little bit. The first part can be easily changed, and that's here the last integral, because as you know, we can make use of the shifting property. So this expression here is exactly the pressure field with the argument r, vector r. So as mentioned here, and that simply simplifies our equation a little bit. So we rearrange all things part by part, use this expression, and then we are ending up with more or less 3 different integral values that we have to finally solve. So we have a volume integral over our source function multiplied by the green function, and we have also a volume integral which is related to the Laplace operator of the pressure or the green function coming from the terms here above. And how can this be further solved? Here we make use of the Green's law of vector analysis, which helps us to replace a volume integral by a surface integral. So we get rid of the Laplace operators here, we get rid of the volume integration, and we are placing the same thing by a surface integration, which, by the way, should normally be much easier, and we're getting a Laplace operator here, a gradient operator instead of the Laplace, so the double gradient, which is in the left-hand side. So, using the green function, the second volume integral, I'm talking about this here, can then be transferred into surface integrals. So at the end of the day, we are ending up with this pressure expression, which is an integration of our volume with the source term, and some other expressions which relate the gradient of the pressure at the boundary and the gradient of the green function at the boundary. So, how can we solve from this our inhomogeneous wave equation? For doing so, I would like to explain those terms step by step. Let's start with the simple one. The first term on this right-hand side is just a volume integral over the source distribution. So that means if, for instance, we have no boundary, we have a free field, this would be absolutely sufficient. The only thing is we take our standard solution, called the green function, and multiply it by any source distribution somewhere in space, could be propeller, whatever, and just integrate with the volume. So we replace our source density distribution, in fact, by many standard sources, which are the point sources. So this is the first step. Good. The next step is to consider the surface integral. We have this gradient at the surface, and this can be rewritten in a different form. So this is the normal derivative, space derivative of the pressure at the boundary, and which is given by this one. But anyhow, this can be interpreted in a different way. We know quite well that there is a formula of this that could this pressure gradient can be converted into a normal velocity using the formula which relates pressure gradient and velocity, and as you might remember, was also used to create the velocity potential. So that means this here, this derivative of the pressure corresponds to this term, but now using the velocity, and the integral becomes this expression. Why is that useful? I mean, in most cases, if sound or let's say acoustic waves are introduced into a cavity, this comes from vibrating surfaces. So that means if I know the shape of the surface, if I know my green function and the velocity at the surface, I have everything that I need to solve the expression how my sound field would look like by using this volume integral, surface integral. Good. So now let's come for the second term, which is another story. So here this means this is the term where the pressure is related to some normal derivative of the green function. This is also quite practical because this is used in practice to fulfill boundary condition. So to fulfill a specific impedance condition. It could be reflecting, hard reflecting, it could be absorbing, but it could also be a specified impedance, as you might know in the reflection case of the transmission and reflection session. Good. So anyhow, there's a naming convention. So this equation here is called the constant frequency version of the Kirchhoff-Helmholtz integral. Wow. I think a lot of mathematics, don't be completely disturbed. If it comes to practical applications, things become much clearer. Just one final remark. This equation here is what is normally used in the boundary element solution. If this is used by discrete meshes. This is what we call a boundary element solution, because we know if we don't have any terms here, we just have to use elementation of the boundary by using those two surface integrals. Good. So now let's come to an example. There's a very practical and very often used Rayleigh example. We will use this extensively here. And this is a special solution of the Kirchhoff-Helmholtz integral, which is applied to just a flat infinite surface, which with an arrangement as given here. So the volume is a kind of half sphere, which is has an infinite radius, so it's in the very, very far away. So our surface integration takes place in the infinite area and then here along the surface. Our vectors, source and whatever, let's say receiver vector, are located somewhere here in this defined volume. And we have an additional source, which is here so-called mirror source position, which is denoted by R index 0 with a dash. And we can use this, I mean, our green function, our classical green function is as the well-known green function as we know it. That's the typical green function, not generalized version. And to create a generalized version out of it, we add a second solution. You might wonder, hey, come on, but this is a solution to a source. Yes, but the point is this source lies outside. So for every volume integral here, it is a part of the homogeneous solution valid in this volume. So this is allowed to generate an additional solution of the homogeneous wave equation to create the general function. What is obvious for our distance, so the distance between R and 0, we have to define different versions, so L and L dash, and R is always the same, only the source position is at some other areas. The first one in the volume, the other one outside the volume. So when we enter this version of the green function into our Kirchhoff-Helmholtz integral, equation 101, we get this expression here, or it's just written it down. To a first extent, we assume that there is no additional source here in the surface area at 1. And second, we just know what is the derivative of the generalized green function here in the normal of the surface. Due to the effect that we have a exactly matching mirror source on the other side, it's obvious that the sum of those functions at z equals 0 will be 0. That's the fact. So that's a derivative. So that means we get rid of this because there's no source in our volume. And on top of that, due to the fact that this is 0 by clever selection of our green function, this is also 0. And just to remember what I said, why we need this term. So by clever selection of the green function, we have automatically fulfilled the rigid boundary condition here. So which is clear, because every source here is reflected, mirrored to a source here. So we have used this mirroring trick to automatically fulfill the rigid boundary condition of this rigid wall. So bringing in typical terms. So now we assume that let's say R0 is could only be here at this surface. In the infinity we neglect that. So z equals 0, which is stated here. That means our green function looks exactly like this, and it is kind of doubling source efficiency because we're doubling the source here due to the hard surface. That means at the end of the day we come out with a so-called Rayleigh integral, and this is a very practical formula for calculating the wave field of an infinite half space with a known velocity distribution at the surface. Given by coordinates x0 or y0, and that means for calculating the pressure field in the half space, we need a surface integration over our half space. We need the velocity distribution, and this is the expression, modified expression of the green function to to calculate this. So, and that means every structure which is somehow flat, it does not have to be perfectly flat, the radiation can be calculated by this. And this is also, as SEA is assuming canonical versions, this is a very helpful version to calculate the radiation of any vibrating structure into far field or into SEA subsystems. Good. Let's come to the first example. And this is a famous piston in a wall. Practical example would be a cylindrical loudspeaker, something that happens quite often. It could be modeled by a piston of radius r, which vibrates with a specific velocity in a rigid wall. For doing the surface integration, we change coordinate a little bit. So from Cartesian coordinate system, we go to cylindrical coordinates at the surface by using this coordinate transform and a different integration surface step. And the receiver coordinates are now given by r, which is now a distance, and the azimuthal angle, theta, which is the angle from the normal vector of the surface. We can write this down by defining this in a different version. We change coordinates, so this is why it now runs from 0 to 2 pi and infinity, 0 to infinity, and we get this expression as a replacement of the Kirchhoff-Helmholtz Rayleigh integral. Good. As this is constant, we just can consider r as the maximum value, because larger than r, everything is 0. Not too complicated for the sound field. In a first step, we do something that some people might know from optics. We use the so-called Fraunhofer or far field approximation. That means that for in the very, very large distances, L, that term here, and R are the same. Practically, this means that we suppose that both vectors are parallel, which is obviously in the near field not the case, but in the far field, if you are far away from the piston, it definitely is the case. In mathematical terms, the far field approximation looks like this. And if we enter this into our above equation, we got this expression, which looks somehow hard to solve, but actually this is not a fact, because this expression corresponds exactly to the definition of the Bessel function of first order. So the solution of this is given by this expression, where you just have quite a Bessel function, angular dependence on the vector, and the product of wave number and the radius of our piston. To give you an overview what that means for typical radiation pattern and logical effects, I just give you some examples here. So if we have a piston that is quite small compared to the wavelength, that would mean that the product Kr is somewhere smaller, slightly smaller than 1, the radiation pattern is similar to a point source, as you can see here. I mean, there's nothing here because we have the half space, but this is like a spherical radiation pattern. When the wavelength becomes slightly smaller than the radius, we are using here a value of the product of 10, we see that there is generated a kind of radiation pattern. We have so-called side lobes, also something that you should also know from optics. And those side lobes become more and more complicated and more expressed if this Kr factor is even getting bigger, meaning that the wavelengths are much smaller than the radius. So this is why any loudspeaker, especially for high frequency, has a directivity, which is something that you normally would not like to have. But you must keep this in mind, that let's say high frequency loudspeaker systems have to become smaller and smaller. I think this is something that you can see at every loudspeaker system. And on the other hand, it's clear why bass boxes are getting so large. Okay, so far for the radiation pattern. The other story, which is very important, we would like to see how is the let's say, what is the behavior of the source itself? So the feedback of the wave field onto this piston, and if you imagine, well, this is defined by the radiation impedance, which is nothing different than the force divided by the velocity, but the force that, let's say, a vibrational surface in the sound field would experience. For getting the force, we just have to integrate the pressure over the piston surface divided by the velocity, which is the same everywhere. And doing the integration for over the radius and creating all the steps step by step, we get this expression here over the surface of the piston. And I would not go through all the algebraic modifications, because to calculate this at the surface of the piston, that's not an easy thing. We have to go to a lot of algebraic modification, which I would not like to show you here in detail. And again, I have to give the reference to my book where this is derived in detail. But when you go all through the modifications, you get this radiation impedance. So a Bessel function of, again, 2kr and kr, plus an additional function, which is denoted by h1, which is so-called Hankel function of first order. When we create the acoustic radiation impedance out of it, so it means we have to divide by the surface here and getting rid of this term, then we get this value. The result for typical values of kr, and the real and imaginary part is shown in this diagram. You see the expectable behavior. So for high kr values, it's exactly equal to 1. So it's like a plane wave radiation. And you have inertia terms, which has the maximum when the value kr is around about 1. For very high frequency, there's nearly no inertia term. For low frequency, there is a specific inertia term. It is interesting to compare this for the same acoustic radiation impedance for a sphere. You see, it is somehow similar. The sphere is slightly higher here for the mass of inertia effects. You see that for high frequency have the same behavior, but what you can also see is that the sphere doesn't have this wavy shape. I mean, this is clearly the interference. This comes with constructive and non-constructive interferences between wave number and the dimension of piston geometry. Good. So what is the final outcome of this? Yeah, as we all know, in SEA we're interested into power input into wave fields, and this can be used by, if we consider a specific source strength. Just imagine this is a volume source, which means that's the velocity times the area. That gives a volume. And that means the radiated power of a piston is given by exactly this equation. And we use here this the source strength in the root mean square value. Okay. To give you, let's say, some ideas about the sound field and, for instance, of the inertia effects, we take the derived radiation impedance and take a series development of the Bessel and Hankel functions. And if we do so, we get this expression, which is valued for kr that are much smaller than 1, so smaller than a half in this case. And if you remember well, the imaginary part of the mechanical impedance divided by omega due to Newton's law must be equivalent to the mass. And if you do so for the top expression, we get that at this area the mass is 8 times this, 8/3 times the radius cube times the density. Or if we just try to visualize this in terms of volume, and we consider, let's say, somehow cylindrical volume, we see that this means at the low frequency, a thickness of 0.85 times the radius is just the air that's moved in front of the piston. So that means at very low frequency, our piston is just pumping air without any radiation. Everyone who have experienced a bass chassis or bass loudspeaker and somewhere at Constance can confirm this because you really feel the airflow, but there's no radiation coming from this airflow. Good. So, so far for simple solution and specific solutions for the pressure. Now I would like to come to some generic formulas and expression how we can calculate the radiation into the wave field, and to rely on some expression that we later need for our coupling loss factor calculation. And before we do so, I would like to do a short wrap up. You remember well that we can use Fourier transform to change the time from the time domain and frequency domain, and to come back from the frequency domain to the time domain. Very important is the impact of the Fourier transform on the convolution. What I'm talking about is, if I take the Fourier transform of a convolution, it corresponds to the product of the Fourier transform of each single function. So a convolution is a very complicated term that becomes very simple in the frequency domain. The same can also be done in the spatial area. So we can also create, let's say, a Fourier transform where we don't have the frequency and the time as argument, but here we use the wave number and the space. So if you remember well, that wave number is the frequency in space, but we have the same analogy like for the Fourier transform in the time domain. So nothing very special. By the way, this should be K, and that was a mistake from my side that I have to correct later. Good. So on top of that, we can also define 2D spatial Fourier transform, which makes sense. We don't have two times, but we definitely have two spatial coordinates here, x and y, and we have two wave number in x and y direction, and they are not the form keeps the same. That means we have here the function in space, and x and y is converted into a wave Fourier transform on two-dimensional wave number space. And again, the back transformation can also be done by a simple formula. The only thing that changes here is that this normalization factor is squared compared to the single space or time version. Regarding convolution, we have the same thing. I mean, our 2D convolution looks slightly different. So we have a double integration, but definitely we have just two vectors here. So it's x minus x0, and here we have just g of x0. So the x0 takes the role of the tau in the convolution here. And regarding the Fourier transform of both equations, we have the same effect. So the 2D Fourier transform of a convolution gives us the product of the Fourier transform in space, wave number space, for the two vectors. Boah. You might wonder, what is this guy talking about and why do we need it? And the trick is the following. We come back to our famous Rayleigh integral. So this is how we can calculate the pressure field of any velocity distribution at the surface. Not the simple one with a piston. Just imagine you have a very complicated vibration pattern of a modal shape or whatever. Then you have to really perform this integration in a maybe painful and complicated way. So if you see here, the L term is R minus R0. So it looks somehow similar to one of the convolution arguments. And here the velocity, this is only an argument of 0. So what does that mean? That means that this expression here is nothing else than the convolution in the two-dimensional space. So we can write the Rayleigh integral as the convolution of the green function. Modified green function is it's a generalized green function of our half space, and convoluted by the velocity distribution. Which anyhow, it's still a complicated method. You have to perform an area integration, which is costly. But if we do the Fourier transform of both expressions, things become much easier. That means our two-dimensional Fourier transform now becomes just a product. So the only thing is that we need the the green function in wave number space, which is this one here. And we need the velocity distribution in wave number space, which can be easily calculated. But the thing is, keep in mind, and that's a trick, our quite expensive convolution or surface integration is replaced by a multiplication. The only thing is that we have to perform the 2D Fourier transform of the expression. I mean, this is always given because it's an analytical expression, but you also need you always need the Fourier transform of your vibration pattern, which might be complicated, but this can also be done by numerical 2D FFTs. Good. So far for radiation. Again, what is important for us? We talk about SEA, which is an energy method, and for energy we have to calculate irradiated power, so understand how energy is exchanged between structures and the sound field. And that's also quite an easy thing. To calculate the radiated power, we have to integrate over all our velocities and the pressure that is existing at the same position of this vibrating surface element. So that means this is our first surface integral. To calculate the pressure on this vibration surface, we again have to replace this by a second volume integral. And this is our well-known Kirchhoff integral. But just keep in mind, at the end of the day, we have to perform a double area integration to get the power of any vibrating surface. The double area integration can become very, very costly. And here we can use the same effect again of the slide before, using the same thing in wave number space, because in wave number space we can get rid of at least one area integration. If you keep in mind, now this second area integration is replaced by a product, by exactly this product. The only thing is that we now have to integrate once over the whole wave number space. And this can be much easier and much faster than other ways to calculate the radiated power. Good. So, in text, the double integral is replaced by a single two-dimensional wave number integration. So we can slightly improve our computation performance if we have everything in wave number space available. Good, so far for the radiated power. Yeah, good. Last remark regarding radiated power, coming to a more, let's say, experimental based quantity. Sometimes it's very practical to understand what is the radiated power of a specific surface velocity. And just imagine that we have any specific vibration pattern and we average this pattern over the surface, which is given by this brackets here with the S denotes, that means that we are just averaging over the surface the amplitude of a vibrating plate, loudspeaker, whatever. And we put this in relation to a plane wave. So if you remember well, the power that is radiated by a plane wave is just the squared velocity using the characteristic impedance multiplied by the surface and 1/2. So this would be the, let's say, reference power of a plane wave radiation with this sound speed, not sound speed, our sound velocity, of the velocity in the sound field. So, and we introduce a quantity that we call radiation efficiency, and this is nothing else than the relationship of the actual radiated power of any specific vibration to this reference power here. That means it's the power divided by the given reference value here. You may wonder, hey, come on, what is the use of this? The use of this is if someone gives you the radiation efficiency of a specifically vibrating surface, you can directly calculate the irradiated power. The only thing that you need is the radiation efficiency, you need the characteristic impedance, a velocity that you can estimate, measure, or whatever, and the surface. So just to give you an idea, I mean, the radiation efficiency could range from somewhere just around 0. If you have a very non-efficient radiator, it goes up to 4, 3 or so. That means you get, in a specific configuration, you can be even more efficient than a plane wave radiation. How this is happening, you will see in later examples, but just to give you an overview, it will hardly be more than 10, and this is more or less the maximum value of radiation efficiency. You will very often use the radiation efficiency for coupling between vibrating surfaces and cavities in SEA models. Good. So far for all the Rayleigh integrals and whatever. Hopefully I have not completely confused you. If yes, please say in the comments, ask me some questions. But also you can go back and repeat it and it will hopefully becomes clearer. But anyhow, please keep in mind those things are very, very important for doing acoustic or vibroacoustic work, because in many, many cases, our work is just calculating the radiated power of any vibrating structure. And this is very important to understand how this works and what are the critical properties and factors in this process. And this is the theory that you need for this. Good. We conclude our fluid chapter with some slight practical things which can be hardly avoided, because, I mean, if you have talked to some people about acoustics, you might have noticed that you're never using quantities like Pascal or pressure or bar, whatever. In acoustics, you mainly use decibel. What is that? Decibel is nothing else than the logarithmic scales of the root mean square pressure squared, again, divided by a reference value. And as this is squared, it could be written in this version, or if we just factor out the square potential, then it would read like this. And the reference value is exactly 20 micropascal. You may wonder, where are these 20 micropascal coming from? First of all, this is in former literature was supposed to be the hearing threshold at 1 kilohertz. Actually, it is slightly lower from newspapers, but this was a created reference value, and this is what is normally used always in typical acoustics. Just one remark: very often the decibel values are compared to values in water for sea mammals. For the value in seawater is different. In seawater is just 1 micropascal, and this has a completely different meaning. Why is it called decibel? It's just multiplied by a factor of 10 to spread the scale, because otherwise it would not be 10, 20, 30 decibel, it would be 1, 2, 3. By the way, the Richter scala of earthquakes is just using a logarithmic scale without the 10. To relate the values of this, here are just some examples. So again, this is the threshold. It goes up to typical interior configurations, library, living room. Noisy things are around 60 to 90, and everything that goes above 100 are dangerous for your ears. So especially if you have exposed to such levels for a larger period, that could be very, very dangerous. However, our ear is capable of hearing this to this. So these are 12 orders of magnitude. That means that our ear is an excellent sensor, and that this is a reason why we need a logarithmic scale. Also very important to understand that linear quantities like pressure, velocity, displacement always use the mean square values. And all the levels and all the decibel values, they always reply to the mean square value. It's always an average value over time. So please, just from my experience, don't use this for amplitudes. It doesn't make any sense, because it always leads to confusion. The decibel is always related to a root mean square value, and this is an important thing to know. It becomes even more obvious for energy and power, because this is, as you know, always must be time averaged, because it's a pulsating quantity. And here we have the same impact, but as all energy and power quantities, they are not squared. They're just used as a linear version, and you use the just the linear version of the logarithm. Nothing is squared, so always 10, not 20. The reference value is 1 picowatt. And you will later learn why this is used by picowatt as a reasonable value here. Good. This decibel scale is also used to relate a ratio of similar quantities. A very important one is the transmission loss. You have seen the transmission coefficient in the transmission reflection chapter between two fluids. And this is a relationship between the transmitted and the incoming power. So incoming here, transmitted, and we neglect the reflected power here. And if we just write this down in the logarithmic value, we call this the transmission loss. You may note that the definition of tau is exactly reciprocal. So this is the incoming divided by the transmission. So this is why we have to use the reciprocal version here and a minus here. Why is this done? The idea is that we would like to get positive values for losses. That's a practical thing. Another thing is, and please don't confuse that, is something that we call insertion loss. And this is also the same. That's also a logarithmic scale in decibel, but now we are comparing situation with and without noise control. So it could be, for instance, the pressure output of a pipe, and then you put something in, a muffler, and the aim of the muffler is to reduce the output pressure. And this is what we call the insertion loss, because it describes the loss of something that is inserted. And this here is this expression. So no longer any power quantities, but two comparable quantities. It could also be vibration, but here in the muffler example, it is the squared pressure. So as mentioned, you may wonder why we have quite a strange reference quantity for the power of 1 picowatt, and what is the relationship to 20 micropascal. And I will just give you a hint why this was chosen, and it really makes sense, but it makes only sense for simple practical reasons. And for explaining this, we just take our spherical source equation. This power radiation of a point source or spherical source, and the pressure, root mean square pressure squared, and somewhere in the sound field is given by this equation. We modify this a little bit, so we divide it by the pressure reference value, and we add a reference surface area. So this is just required to get the units correct, as you will later see. If we take the decibel out of this, and this is just written here in this equation and carefully distributed, we will have this first term here, which is just the pressure level as it is defined. We have this term here, which is somehow related to the power level, as I will later show, but divided by this expression, which could play the role of the reference value, and something that has to do with the propagation, because it's a spherical field and we have something that is depending on the distance. Without any, we just choose that this is 1 square meter to keep things simple. And if we do so, we get this expression. So this term here can be described as the reference power. This is just a geometrical factor coming from the 1 divided by 4 pi. And this is just the distance factor, 1 square meter divided by the radius or the distance. So now you understand why we needed this reference value. This was just required to get the units right, because we have the radius here, and you cannot divide 1 via area. We need a reference area, which we take the area 1 square meter. When we check what is here in this denominator, we see that our reference power should be something like this. It's a reference pressure divided by the characteristic impedance times our chosen reference 1 square meter. And if we do so, we get this expression. That means this is the power level. This is round about 11, and this is just 20 logarithm of the radius divided by meter. And if we then enter typical values for density and speed of sound, and the reference pressure, which is 20 micropascal, you will see that this is more or less exactly 1 picowatt. The thing is that the picowatt and by selecting this 1 picowatt, it matches perfect to the power in combination with the characteristic impedance. That's clear. It only works for air. It doesn't work for any other medium, or it has to be a similar characteristic impedance. So this is why 1 picowatt is the reference for power, because just look at the equation here on top. The pressure level is the sound power level minus 11 minus a simple logarithmic expression. So it means if you have a point source, or if you have a kind of point loss engine or whatever, you can easily calculate the sound pressure level if you know the source power level. In some equations you will find something like 8 or 5. The reason is, if this is a half space, it will be 1 divided by 2 pi. That means it will be 3 dB less. If it's a quarter space, it will be 5, and so on. So you can at least adapt to the kind of exterior field that you are using. Good. This is a table that I will not explain in detail. Just one remark from my side. You will find such, let's say, source and whatever formula sheets later on my website. So just look at that, where you will find some useful formulas. Please really keep in mind those formulas to relate the source power to the source strength for a monopole, for a breathing sphere, for a piston. Such things are very, very practical, because you need this very often to understand what will be the sound field of a specific sound source in a technical configuration. So those quantities are quite helpful there. Good. To conclude, we have really done a very rough chapter with fluids. And what have we done there? We have derived all the wave phenomena and relationships and wave equations that relate the pressure of a sound field. We have found a lot of expressions that relate pressure, sound velocity, power, and energy to understand what are the characteristic quantities in our sound field. We also have learned that the main quantity that is to link the pressure and the sound field and power and energy and so on is the acoustic impedance. If it's a plane wave, it's a characteristic acoustic impedance. So meaning it's a ratio of the pressure by the sound velocity. We have treated the transmission between different fluids, and this is the first occurrence of coupling wave fields, then exchanging the energy between wave fields. And also here again, this how things are coupled, how the energy is coupled, the determining quantity is the radiation impedance. It's not the speed of sound, it's not the density, it's always the combination or the product of them, it's the radiation impedance. Good, so that's it from my side. Hopefully you have not completely smashed it, but again, it was hopefully clear. If you have some questions, just ask in the comments on my website or down the video. In the next session, we will come to waves and structures. Also very complicated things, but here we will not go too much into detail. So in the waves and structure, that is much more important to understand what is the difference of wave propagation and structure, because the nature is much more complicated. There are much more kind of waves. We have you have some frequency dependent dispersion effects and so on and so on. This means you have to get a basic idea about how waves propagate in structures to do good vibroacoustics. Have fun and see you next time for session number 10.